Hello, my name is Rudy, and I'll be talking about how to build state-space models with inspirations from convolutional neural networks. To do so, I'll also introduce the topic of optimal tensor contraction. So our story starts with matrix multiplication. Here we have three matrices, a small one, a medium one, and a large one. Because matrix multiplication is associative, we have two orderings to perform the operations in. For the first ordering, we begin by multiplying the two smaller matrices in the bracket, giving us an intermediate Brown matrix. Then we multiply the Brown matrix with the large green matrix to finish off the operations. For the second ordering, we multiply the two larger matrices first. This also gives us the same result, but now the compute cost is almost 10 times more expensive. This makes sense because we're generating a large intermediate Brown matrix, which is bad for compute. So we see that even though the two orderings gave us the same results, they're definitely not the same in terms of compute costs, and the first one is much better than the second one. Now let's go a step further and look at generalized matrix multiplications or tensor contractions. Here we can have multiple tensors and each tensor can be high dimensional. This includes most neural network operations such as CNNs, SSMs, and attention. Here we use a visualization called a tensor network. It is basically a graph and each node is a tensor and each edge is a dimension. Taking the previous matrix multiplication example, we have three matrices A, B, C as nodes and four dimensions I, J, K, L as edges. The dimensions j and k are being summed over, so they are represented as inner edges. This means that the two outer edges, I and L, will be part of the output tensor. As we see in the previous example, every time you contract an edge or sum over a dimension, you introduce a compute cost. To reformulate this in the language of tensor networks, the compute cost is just the weight of the edge being contracted times all its neighbors. For example, if you contract the edge j, you need to look at all the neighbors I and k as well. And we see a compute cost of 10 times 100 times 1,000. To understand this a bit more, I'll show you guys a fun example where we have three tensors being contracted in this triangle pattern. First, we contract the top inner edge connecting A and B. We multiply the weights of all adjacent edges shown in red, which gives us this compute cost. So now we see the tensor A and B are merged because they are contracted into an intermediate tensor, and we call this AB. We can then contract the two inner edges, both having weights of 2, and again take the product of all edges shown in red to get the compute cost. Finally, we get an output tensor with three outer edges, which represents a three-dimensional tensor. So now you may wonder why we choose to contract the top inner edge first, since it has a large weight of 100, but actually if you try to contract any of the other two smaller edges first, you can verify that the second stage compute cost will be super expensive. Basically, if you try to do greedy optimization in the first contraction stage, you may get very bad compute costs in the later stages. And this is really the crux of tensor contraction, which is to find the optimal ordering of contraction. Now moving on to convolution, which has this sliding window structure, but if you're familiar with the convolution theorem, you know that convolution is just an element-wise product in frequency space, which is actually very straightforward, so we can easily map it to a tensor network. So now having the convolution part figured out, there is actually an additional structure of CNN that we sometimes forget, and that is a channel interaction structure. But this structure can be easily added to the tensor network as well. For example, if you look at the simplest depthwise example, which C is a channel index, you get two independent branches, one for channel and one for frequency, which you can see in the tensor network figure. Now moving on to SSMs, which basically behaves like a CNN because they can generate a convolution kernel via the impulse response. The only difference is that they have another dimension of internal states. So there is one more dimension to look at. This is where tensor networks can really help you out with this complexity. Actually, if you're familiar with the original S4 paper, the authors already realized back then that there is an underlying depthwise convolutional structure. Here, we just generalize this understanding to fold convolution, group convolution, and bottleneck convolution. This bridges the gap between CNNs and SSMs, and we call this formalism Centaurus. You can check out my paper to see the story behind this naming. Okay, so here we see a tensor network representations of various CNN structures applied to SSMs. Notice that the internal states are indexed by n and are always represented as inner edges, because they are never exposed to the output, being internal states. On the other hand, notice that the output channels are indexed by j and are always represented as outer edges because they are obviously part of the output tensor. You can also see other output edges like G standing for group and F standing for frequency. So how do we take a CNN and map it to a SSM in practice? It is actually not super hard. First, you take your favorite CNN, which can be off the shelf. For example, my favorite network is MobileNet V2 because it has a unique bottleneck structure. So now I take the core bottleneck layer and map it to a tensor network, or an Einstein expression as shown here. Since the tensor dimensions are usually fixed during training, you can just do an exhaustive search to find the optimal contraction order, and this is just a one-time cost you pay upfront. Okay, so that was a lot of theory. Let me show you some empirical results. As I mentioned, we're basically taking inspirations from existing CNN networks. For example, here we take MobileNet v2 and convert it into SSM. But instead of doing computer vision tasks like image classification, we can apply it to speech recognition, which is a form of sequence modeling, something that SSMs are very good at. I just want to emphasize that we're not doing any attention mechanism here, but it still managed to perform pretty well. Here's another example where we take a narrow glass CNN network, which is typically used for object detection and segmentation, but here we convert it to a SSM and use it for raw speech enhancement instead. So in summary, even though we think of CNNs as mostly network for computer vision, I think their design philosophy easily carries over to SSMs as well, in particular for sequence modeling. So thank you for listening to my talk, and I hope you found it useful. Feel free to check out my GitHub and Google Scholar to learn about some of the other stuff I do.